This is a short video about 1.12 in Stein's elementary number theory book about the greatest common divisor. Probably break this into maybe 2 or 3 videos because it's kind of a long section. So to jump right in, what's the definition of the greatest common divisor of 2 integers? The notation for it is going to be GCD of A, B. It's kind of like saying GCD is a function with 2 inputs. And what's it going to be defined to be? It's going to be the largest of any integer that divides both A and B. And here's kind of the weird fringe case. We'll say the GCD of 0 and 0 is 0. So even though it doesn't make sense to divide by 0, we'll just say the GCD of 0 itself is 0. So for example, what's the biggest number that divides both 6 and 27? Well, it would be 3. And similarly, what's the biggest number that divides both 1 and 2? Well, 1 is the biggest number that divides both of them. Notice here that's, I guess, the largest integer where D divides both of these things. We could say that the GCD is always a non-negative number. So what's maybe a good fact for the GCD that we'll need, particularly toward the end of this video? So for any 2 integers A and B, the following are all the same thing. So how you should read this, the GCD of A and B is the same if you've switched B and A around. So in other words, the biggest thing that divides A and B is the same thing as the biggest thing that divides B and A. That's not too deep. Also, doesn't matter if you throw some different signs on A and B. GCD doesn't care. But then here are some of the more useful ones that we'll need later on. The GCD of A and B is the same as the GCD of A and B minus A. So of A and maybe some kind of linear combination of B and A. And then it's the same thing as the GCD of A and B plus A. Again, just some different linear combination of A and B. So what we'll do is, just to get used to how some of these proofs go, we'll prove that GCD AB is the same as GCD of A and B minus A, just like Stein says we'll do. And remember, a way to do that, to show that 2 numbers are equal to each other, the first thing we'll do is show that one is less than or equal to the other, and then we'll follow that up with showing that the other one is bigger than or equal to the other. Therefore, if both of these things are true, that implies there's an equality. That should feel a lot like showing 2 subsets are the same. You show two sets are the same. You show that like A is a subset of B, and then you show that B is a subset of A, and if both of those happen, that means A is equal to B. Works the exact same way with numbers. So how will we do this? Well, suppose that you had some number D that divides both A and B, and then now what does that do? By hypothesis there, that gives us a definition to start playing with. Well, if D divides A, well then D times some number C1 is A, and if D divides B, by definition, that means D times some number C2 is equal to B. And now what we'll do is, let's think about what's this expression B minus A look like? And let's plug in our expressions for A and B. And so B minus A looks like DC2 minus DC1. Factor that D out, and if you think about, what does this say? This says B minus A is equal to D times that. Of course, that means that D divides B minus A. Now let's recap a little bit. We just showed that any number D that divides both A and B also has to divide B minus A. So we could pick this up down here. So any number D that divides both A and B also divides B minus A. So in particular, the greatest common divisor of A and B, that's such a D, it has to divide B minus A also. So what can we say then? Well, then the greatest common divisor of A and B, which could be that D, has to be less than or equal to the greatest common divisor of A and B minus A. So in particular, right, all common divisors of A and B have to be common divisors of A and B minus A. Okay, that's pretty cool. So that shows this inequality here. And again, we just need to show the reverse inequality is true as well. And that's pretty quick if you just reverse the roles of replace A by negative A and replace B by B minus A, and do pretty much the exact same argument to try to show that the GCD of A and B minus A is less than or equal to the GCD of A and B. It's a very similar argument. And of course, now that we have this less than or equal to here combined with this one here, that's how we get the equality here. So we'll use that a little bit later. Remember, lemma 1.19. I'll use it again toward the end of the video. What we could do, we could extrapolate a little bit. The GCD of A and B should be the same thing as the GCD of A and B minus any multiple of A. And so how would we do that? Well, the GCD of A and B is equal to the GCD of these 2 numbers, and that is just by the previous lemma. But what if I subtracted another multiple of A? So if I subtract A again, that's this. And so lemma 1.19 tells me that these 2 are the same. What if I subtract A again? That would be b minus 3a. Then I would get that the GCD, this is equal to the GCD of a and b minus 3a as well. So I can just do that as many times as I want. Well, how many times do I want to do it? Well, I don't know. Looks like we said n here. So they're all the same. So scrolling down a little bit, we'll come down here to what we might call the division algorithm. And this is also something that should not be new. It's probably something that you use all the time. In particular though, if you've got two integers a and b, and let's say b is non-zero, then there are unique integers q and r, where r has to be non-negative, and at most it can be the absolute value of b. But what can you do? What's the punchline? A is equal to b times q plus r. So let's write something down. So something like, what if a is equal to 7, and let's say that b is equal to 5. So what I'm saying to you is 7 should be equal to 5 times something plus something else. And the caveat, or what you got to be careful about, is the plus part here can't be negative. So what can I do? Well, this would have to be 5 times 1 plus 2. And of course, hey, that's the quotient, and that's what q stands for. And 2 is the remainder, and that's what r stands for. Now, what else do you have to be careful about? Something like negative 6. Let's say a is negative 6, and let's say b is 5. After all, these are just integers. I didn't say they had to be positive. And maybe what you'd like to do is say this should be minus 1, and this should be plus negative 1, but that won't work. I can't have minus 1 for r. So what we've got to think about is, well, there must be a different q then. And of course, that different q would be minus 2, and I'd have to do plus 4. So in that case, we'll call the quotient negative 2, and this remainder here 4. So again, we have this kind of stringent hypothesis that the remainder has to be a strictly non-negative number. If you've taken like an intro to proofs class, of course we're saying this is the same thing as trying to say that negative 6 is equivalent to 4 mod 5, something like that. We'll use that language a little bit later on. If that made no sense, don't worry about it. So what's the proof of this? How do I know that I could do this? This is kind of a famous result, and we'll need it certainly. So what we're going to do is, well, for simplicity, let's say that both a and b are positive here. So we'll only do that case. There are some other cases where what if they have different signs, or what if they're both negative? So what we'll look at is, let's say q is the set of all non-negative integers n, such that a minus b times n is not negative. Okay, so a minus b times n, what does that kind of look like? That kind of looks like if I was going to move bq to the other side of this. So what we're looking at is, what are all the expressions r, which kind of think about, going to be kind of remainders. We're looking at all those expressions, but in particular, to make sure that they're all non-negative here. So I've got some set of non-negative integers n that make sure that this is not negative. And so, well, q has to be non-empty, so 0 has to be in q. In particular, how come is that? If I plug in 0 for this n, you just get a. And if a is positive, well then this expression is not negative. So that's why 0 is in there. And then what else? It's got to be bounded because, well, if n is larger than the fraction a over b, well then, oops, didn't mean to do that. If a is larger than that fraction, then a minus bn is negative, which doesn't satisfy this. So it's got to be bounded. There can only be I guess there has to be a biggest one, is what I want to say. So what we're going to do is, let's say q is the biggest one. So q is the largest one. So q is the largest element such that a minus bq is still bigger than or equal to 0. So that means if you did the next q, if you did q plus 1, then a minus b times q plus 1 would be negative by hypothesis here. So keep that in mind. Now what we'll do is we'll look at the expression. Let's look at the expression a minus bq, where q is that largest element. We'll call that r. So notice here, again, that r is going to be a minus b times q. And notice that that's less than b. Otherwise, q plus 1 would have to be an element of b. So you can write that down and chase through that to convince yourself that r has to be less than b. And what we're setting ourselves up for is to make sure that our r really does satisfy these conditions here. So what we just showed is that there definitely exists a q and there exists an r. And we kind of made the r from the q. So if this is what r is equal to, then we'll just solve that thing for a, and we've got our expression. So we showed that two such integers exist. Now what we need to show is that, well, there's only one such q, and there's only one such r. So this is a uniqueness proof, and they kind of always go the same way. So to prove uniqueness, let's say you had two other numbers, q prime and r prime, that also satisfy this conclusion, where I could write a as b q prime plus r prime, and r prime satisfies this condition here as well. So what would happen then? Well, if q prime is a number that's in q as well, capital Q, then r prime, I know by definition, it has to be a minus b times q prime. That's a non-negative number by hypothesis. So what can we say then? Well, then q prime has to be less than or equal to q, since we assumed that q was the largest element of big Q. So what does that allow us to do? Well, q prime is a little bit less than q, so that means that, well, q prime should be q, but a little bit less, is what this says here. So for some integer m and some non-negative integer m, so if these are not equal, well, then this has to be strictly bigger than 0. So in particular, m is bigger than or equal to 1. And let's think about what happens then about r prime. By definition, r prime is this, but now let's plug in our expression here for q prime. So our expression for q prime is right here. We'll take that and we'll plug it in. So I guess really I plugged it in here, but it gives me this. I think you see what I'm saying. And now if you distribute that b through there and regroup some things, notice that this much here is this r, and r plus b times m, everything here is non-negative, so that's at least b. What does that say though if you kind of chase through it? R prime is bigger than or equal to b, which is impossible, right? We assume that r prime had to be strictly less than whatever b is by hypothesis, if r prime was such another number. So what we just said is we said that this q prime not equal q, that's impossible. Well, what's the opposite of that then? Has to be the case that q is q prime, and then by definition r prime has to be the same as r. What we'll do is we will use that, we'll call that the division algorithm. And so it's really just long division, more or less. Most of the time for us, it'll just be long division like you learned in school. What we'll do is we'll actually use that to try to compute the GCD of two numbers. And so to illustrate that, let's say I wanted to find the greatest common divisor of 2,261 and 1,275. So what we'll do is we'll just do this number divided by this number first. And if I did that, I see that, well, 1275 goes into 2261 one time, and the remainder, what you have left over, is 986. But now here's something that's kind of cool. If you had a number d that divided both of these to start with, think about if you move this to the other side. Then you could factor d out of their difference. So then d times some junk is 986. Well, that says that d divides 986 as well. So in particular, the greatest common divisor of these two numbers is also going to be a divisor of 986. And vice versa, or maybe vice versa is maybe not the right word. Conversely, on the other hand, if d divided, say, both 1275 and 986, in that case, if d divided both of these, you could factor d out of these, and that says d divides 2261 as well. So what am I trying to say to you? I'm trying to say to you that the GCD of 2261 and 1275 is the same as the GCD of 1275 and 986. So what we'll do then is we'll just apply this logic again. Why don't I do 1275 divided by 986? That computation's right here. 986 goes in there one time, and the remainder is 289. And now I'll play the same game. Right? So the GCD of 1275 and 986 should be the same as the GCD of 986 and 289. And what we'll do is we'll keep going. Divide 289 into 986. That's this line right here. Now we'll focus on 289 and 119. We'll do a division again. That's this line right here. Now we'll focus on 119 and 51. And I'm going to keep going until I get to this line here. Notice that in the next line, when I do 51 divided by 17, I get a remainder of 0. And so in this case, that's 17. That's where I stop at. 17 is going to be the GCD of all pairs of numbers in my computations. In particular, it's the GCD of the thing I wanted to begin with. Now this is an algorithm to compute the greatest common divisor, and in algorithm form, by the way, algorithm is just like a series of steps to compute something. So we just said to track through here, you can assume A and B are positive numbers. Use the division algorithm a whole bunch of times to get your quotients and remainders. Anytime you get a remainder of 0, that means you're done. And your output then, the GCD, is going to be B. But if you don't get a remainder of 0, you're going to switch A to be B, and you're going to set B to be R, and then repeat. So to give you an example of what that says again, if I've got 15 and 6, I want to know their GCD, you would say, well, 15 is equal to 6 times 2 plus 3. Because my remainder is not 0, I'm going to go to step 4 here. So what I'm going to do is I'm going to focus on 6, what B was, and 3, what R is. And so this says to set A to be B, so that's this right here, and set R to be, set B to be R, and then do the division algorithm again. So 6 is equal to 3 times 2 plus 0. Now that you're done, you've got a remainder of 0. What this says is that as soon as you get a remainder of 0, the output is B. So B is 3, and that's the GCD of 15 and 6. We could do it one more time. The GCD of 150 and 60 should be equal to what? So if I do the division algorithm, 60 goes into 150 twice, the remainder is 30. Now I'm going to make this on this side, and I'll put 30 as my new B. And when I do that, I see 30 goes in there twice, the remainder is 0. Therefore, this B here is my GCD of my original two numbers as well. And by the way, Sage can do our GCD computations very, very quickly as well. So what we did up here is called the Euclidean algorithm. Euclidean algorithm. There's an A there. That's really bad handwriting. Oh well though. But then Sage just has this built-in GCD command, which is fairly fast.